Screencast covers the brief history of the importance of collisions in physics experiments. This screencast accompanies my lecture on this topic. I show this PowerPoint presentation in class. The first experiment of its kind was performed by Ernest Rutherford, a New Zealander living in Great Britain at the time in the early 20th century. In 1911, he performed his famous gold foil experiment. In doing the experiment, Rutherford discovers that collisions provide the best means of probing the inner constituents of matter. Here are the basic details of the experiment. What he did was he took a source of alpha particles. Alpha particles are helium-4 nuclei that are naturally emitted by uranium as it breaks down into lighter elements. This process is known as radioactive decay. At the time, in 1911, radioactive decay was not understood. However, Rutherford realized that he could use the alpha particles, which are naturally being emitted by the uranium, as a means of probing the inner constituents of matter. So right here is his source of uranium, and he actually surrounded the uranium by a lead box. Lead is really dense, so it's not going to let subatomic particles through, but he did have a hole cut into it into the side here on the right-hand side. This then allowed a beam of alpha particles to emerge from the uranium. That beam of particles was then directed to its target. The target was the very famous thin gold foil, and it truly was thin, by the way. It was only a few hundred atoms thick. The reason why he used gold is because gold is a very soft metal and it's very malleable. This means that it can be shaped very easily, and it can also be shaped into very thin sheets. Okay, now with respect to the alpha particles, if you basically take these high-powered bullets, if you will, and then fire them at tissue paper, that's basically the analogy that Rutherford himself used, then you would expect all of those high-powered bullets that are traveling at a high speed to go right through the tissue paper. With respect to the alpha particles, that's pretty much what happened more than 99% of the time. However, less than 1% of the time, the alpha particles would appear to hit something deep within the gold atoms themselves and then get deflected off to the side. In other words, a collision was occurring. How did he detect these deflections? How did he detect the alpha particles going through the gold foil? Well, he surrounded his target here, the gold foil, with this screen. This screen is coated with a chemical compound called zinc sulfide. Zinc sulfide fluoresces. It gives off light when struck by charged particles. Okay, the alpha particles themselves, by the way, are positively charged, so they're being repelled by a positively charged target here within the gold atoms themselves. By examining the mathematical details here of the collisions, Rutherford basically reached three conclusions. Number one, the target, whatever it is that's being hit by the alpha particle, is extremely small compared to the overall volume of the atom itself. The volume of the atom is mostly empty space. To give you an idea of the size of the target itself compared to the overall volume of the atom, picture the overall volume of the atom as the quad, for example, here at school. And then the target that is being struck within the gold atom itself would be about the size of a grain of rice. So this is how we know, for example, that the volume of the atom is mostly empty space. Number two, as I mentioned earlier, the target, whatever it is that's being struck by the alpha particle, is also positively charged because it is repelling the positively charged alpha particles. And then third, the target must be very massive. It must be very massive in the sense that it contains most, if not all, of the mass of the atom itself. Pretty obviously, these three conclusions led Rutherford to conclude that what he had discovered here is now referred to as the atomic nucleus. So in performing this experiment, Rutherford basically hits upon the only experimental means that we know of probing the inner constituents of matter. The basic idea is to collide matter together at extremely high energies and then examine the details of the collisions themselves. So then therefore, subsequently, going forward from the Rutherford experiment, from throughout the 20th century and into today, these types of experiments have continued. Okay, now in the years following the Rutherford experiment, up until about the Second World War or so, these types of collision experiments took place on a small scale, and they also took place at relatively low energies. Rutherford himself did not use electric fields to accelerate the alpha particles to higher energies, but subsequent experiments did. And as they conducted these experiments, physicists once again did this on a small scale. These types of experiments basically took place on countertops. Okay, now over the course of the 1910s and the 20s and into the 30s, these types of experiments then led to our understanding of the atomic nucleus. Atomic nuclei are composed of two different particles, protons and neutrons. Protons of a positive charge have the same amount of electric charge as the negatively charged electrons. Neutrons are neutrally charged. We also discovered what makes an element a particular element, and this is described by the atomic number. The atomic number on the periodic table refers to the number of protons making up the nucleus of an individual element. This then defines what the element is. So, for example, hydrogen contains one proton, helium contains two protons, lithium contains three protons, and so on within the nuclei of those atoms. So the basic layout of the periodic table was understood by studying the atomic nucleus. Also, during these types of experiments, we discovered that certain types of elements come in several different varieties. These are referred to as isotopes. So for example, there are actually three types of hydrogen. Most of the hydrogen in the universe, what is called hydrogen 1, has a nucleus that just consists of one proton. But there are small amounts of what are called hydrogen 2 and 3. Hydrogen 2 has one proton and one neutron. Hydrogen 3 has one proton and two neutrons. So all these details of the atomic nucleus were basically being figured out in these types of experiments up until the Second World War. The experiments that were performed during this time accelerated charged particles in a line. They used electric fields to do so, and they would then slam those charged particles into stationary targets. This type of an accelerator, that is, a device that does this, is referred to as a linear accelerator because you accelerate the particles into a line. Okay, now just prior to the Second World War, we now get to this gentleman here, an American physicist named Lawrence. Lawrence invents what is called a cyclotron. A cyclotron is a device that uses magnets to steer charged particles along a circular track. Electric fields then accelerate the particles to extremely high energies. So the basic idea is to very simply have the charged particles circulate like so here on this circular track. You then accelerate them to increasingly higher and higher speeds as you go, and then what you do is you direct those charged particles off to the side and slam them into a stationary target. Or in the case of having one beam of particles move in one direction, that would be, say, positively charged, and then another beam of particles move in the other direction, that would, say, be negatively charged. You can then reach extremely high energies and then slam the two particle beams into each other. Lawrence's first cyclotron, as you can see here in this photograph, basically fit in the palm of his hand. Okay, and then the Second World War happened. The Second World War was not just a watershed event in human history, it was also a watershed event in the history of physics. When it comes to the Second World War, basically the Allies strategically won the war because of two inventions that came out of physics research. The first invention was radar. Radar allowed the British to win the Battle of Britain in 1942. 1942 were very dark days for the Allies. The United States had entered the war, but it didn't have a chance as of yet to get its armies and materiel across the Atlantic Ocean. Basically, Great Britain stood alone. The continent of Europe had basically been overrun by the Nazis. Now, in order to soften up the British, basically what the Nazis then did as they planned to invade Great Britain was they sent their planes out over the English Channel to basically bomb the British cities. Well, the British were able to set up their defenses ahead of time and repel those planes because they used radar to do so. Basically, radar allowed the British to win the Battle of Britain, preventing the Nazis from invading Great Britain, and that bought the Allies time. And then secondly, of course, we have the atomic bombs that were used on the Japanese cities of Hiroshima and Nagasaki, which then ended the Second World War. Periodically, you will hear some attempts at revisionist history when it comes to the end of the Second World War. Sometimes some people and historians consider the use of atomic weapons at the end of the Second World War to be somewhat controversial. That's not the case, however, and the reason for that is because the use of those weapons, as horrible as they were, ended the war quickly. If we did not use atomic weapons at the end of the Second World War, then in the spring of 1946, the United States had plans to invade the home islands of Japan to bring about the end of the war, and that would have resulted probably in millions of casualties. Okay, now I'm going to go ahead and conclude this here as part one of this screencast. What happened after the Second World War, I'll get to in part two.